All right, let's get started with Lesson 13, Titrations Part 2. Now, besides using a pH indicator or pH paper to determine the pH of a solution, we can use a very nifty tool called a pH meter, which is pictured here in front of you. pH meter works like this. You have a special electrode called a pH electrode, surprise. And that pH electrode is put into the solution that we want the desired pH for. The pH probe or electrode is going to do a series of chemical processes that will gather data to send to a computer, which is the meter part, and the computer will then display the pH of the solution. The pH meters are very accurate and very reliable devices. However, they are pretty expensive. pH meters are very useful when we're doing titration, so we want to monitor the change in the pH during the titration as we add the base to the acid, which you can see diagrammed here. So we have our pH or our titration set up where we have a burette with a base in it, sodium hydroxide. And then we have a container, a beaker here, that contains our acid that will titrate. So we add the base from the burette, as you know, into the beaker that has the acid, and we do so drop by drop. And as we're adding base to the acid solution, we're going to monitor the pH change with the pH meter. We put the electrode into the solution, and the data is fed back to the meter, and you can record the pH. Really, the kind of data that we typically collect during a titration of such is we take the volume of the base added, and we take the corresponding pH of that. So we usually have two columns. And so, of course, initially there's no volume added from the base, and so the initial pH, so we'll say like pH of 1, would be the pH of the initial acid in the beaker. But then as we start adding volume, like 2 milliliters, we should see the pH begin to go up, okay? And that's kind of the data that we take using a pH meter for titration as this. Okay, so what do we do with this data? Well, we create a graph from the data, a graph that looks very much like this listed in front of you, which is called a titration curve. And we take the volume of the base, the sodium hydroxide in this case, added, and the monitored corresponding pH. And we typically, in a titration curve, get a curve very similar to what you see right here. What you're going to have to do is look at these titration curves and interpret them and understand some specific points in the titration curve that you need to know and understand. Okay? So what we're going to do now is we're going to go through the various titration curves of various titrations that can be conducted. Okay, so the first one we're going to look at is a strong acid and a strong base titration. In this case, we're adding the sodium hydroxide or the strong base. In fact, let's do the reaction here. We're going to take our strong acid and our strong base, sodium hydroxide, and of course we get a neutralization reaction of water and salt to be formed here. So we're essentially going to add the strong base to the acid. So the burette will have the sodium hydroxide and the beaker will have the hydrochloric acid. Okay, so we collect the data of pH versus the base that we add. So on our y-axis we have pH. The x-axis will have volume of strong base added. All right. So when we take the data, we get a typical curve that should look very similar to this. All right. Actually, I should make this a little bit better. Let me actually start all over. Make this curve. There we go. All right. So this is a typical curve that we get for a strong acid, strong base. And we're going to have some points here. This is point 1. We'll have point 2, point 3, and point 4. These 4 points on this titration curve, we need to identify their meaning and understanding, okay? So point 1, which I'm going to write here, point 1, should be the pH of the strong acid. All right, so typically it's a strong acid. We might see it at a, let's say, a pH of 1 is what we're starting with here on our titration curve, okay? The initial pH of the strong acid. And then what we're going to do is we're going to start adding base to the acid, and we should start seeing a increase in the pH by adding the base as the base reacts with the acid and is using it up. So at point 2, essentially we're going to see only the pH is going to change really gradually, right? We don't really see a large increase of the pH, especially from a pH 1 to whatever this range is going to be. There's not much of a change in the pH. It's a very subtle change. But as we get closer and closer, let me redraw that. As we're getting closer and closer to point 3, the pH begins to climb fairly dramatically. In fact is, right before we get to point 3, there's a huge jump or spike in the pH. In fact is, most likely, we're looking at this point before we get to this big jump. This might only be a pH of 3 or 4, maybe even less than that. And then all of a sudden, woof, we get that big spike at that point, okay? So what is point 3 exactly? What is the meaning behind it? Well, point 3 is the equivalence point. It represents the equivalence point in our titration, all right? Now, of course, at the equivalence point for a strong acid and a strong base, all of the acid and all of the base should be completely used up at this point. So the only thing that remains at the equivalence point would be our salt, sodium chloride, so we'll just put salt in general, and the water. That's the only thing, 2 things that exist at this point. So the question is, what affects the pH at the equivalence point? What can we do to predict what that pH might be? Well, the salt might affect the pH through salt hydrolysis. So we have to consider that. So we'll look at our salt, and we have sodium ions and we have chlorine ions. The sodium is the positive ion, so it would be the acid, and the chlorine ion is negative, so it would be the base. Now, looking at these two and doing our test, we would find that sodium is not reactive with water and chlorine ions are not reactive with water, so the salt should not change the pH at all. So what affects the pH then would only be the water. And if you recall, water reacts with itself to form hydronium ions and hydroxide ions. All right? So at the equivalence point, we should have equal amounts of hydronium ion and hydroxide ion. Okay? So therefore, the pH should be neutral since the hydroxide and the hydronium ion are equal. So therefore, at the equivalence point, at this point right here, drawing across, that should be a pH of 7. All right, for a strong acid and strong base titration at the equivalence point. All right, so that's probably pretty easy to understand. So what happens at point 4? Well, at point 4, we've added a lot more base, a lot extra base. And so at this point, we have no more hydrochloric acid. It's all gone, completely gone, used up. But now we're going to have some excess base added. All right, so what we've done is we've basically overshot the equivalence point, and added an excess amount of base. So at 4, that would be the pH of our base, excess base that we have left over. All right, so those are the 4 points on the pH curve here, or this titration curve for a strong acid and strong base that you need to know. All right, now let's go to a different titration. This time we're going to use a weak acid and add strong base to that weak acid. So for instance, let's use a real weak acid. Let's use CH3, COOH, that's our weak acid, and we'll add it to our strong base, sodium hydroxide again. And again, we should get a neutralization reaction of water plus our salt, which will be sodium acetate. All right? So the data that we collect, we would graph for this titration. Let me erase this. All right, so again, we have pH, and then we have volume of strong base added. All right, so now what would our titration curve actually look like now? Well, first of all, there's going to be some differences than what we saw in the previous titration curve. We're going to start a little bit higher in the titration, and we're going to get this gradual increase like so, and then we're going to see our usual spike, and then something like that, okay? So again, we're going to have some points here, point 1, point 2, point 3, and point 4, okay? So let's identify all of these points, okay? So point 1 is going to be the pH of the weak acid. All right, and since it is a weak acid, it's probably going to start higher as pH than pH 1 as indicated. So let's say this is a pH of 3 compared with our 1. So it's strong acid. Remember, it's going to start its curve way down here. Okay. So there's one difference. All right. So now, because we have a essentially a weak acid here, during the course of the titration, we're going to actually create a buffer between the weak acid and its conjugate base. Now, the conjugate base is going to be the acid. Oops, erase that. It's going to be the acetate ion. So this part that I underline here, that's the conjugate base of our weak acid. Okay. And initially here, as we start adding sodium hydroxide, it's going to get to that point where we create a region or an area that is known as the buffer region. And that is right in this area here, is known as the buffer region around number 2. And the buffer region is really where the buffer exists during the titration. So what we are going to see is a resistant in the buffer region, a resistant of the change in pH, which is indicated by this gradual increased slope here. All right. So at point 2, let's identify point 2. I'm actually going to bring point 2 out here so we can write a little bit. This again is where the buffer region exists. And specifically at point 2, this would be halfway that should be an H. Rewrite that. Okay, so this is halfway to the equivalence point. Okay, I'm kind of writing small here, but to fit a lot of room information here. So this point 2 is halfway between the equivalence point. But what else is interesting about this is the point at point 2 where the weak acid concentration is equal to the conjugate base concentration. They're equal here. So the concentration here is equal to the concentration of the acetate ion at this point, which means there's a 1-to-1 ratio that exists here. And so if you think of the Henderson-Hasselbalch equation, this is exactly in the buffer region where the pH is going to equal to the pKa of our weak acid. Now this is a very important point in the titration here. Make sure you understand that point 2 is where the pH is equal to the pKa, and the concentration of the weak acid is equal to the concentration of the conjugate base. We have that 1-to-1 ratio, all right, at that particular point. And it's also halfway to the equivalence point, okay? So what about point 3? Well, point 3, again, is going to be the equivalence point here. Just like we saw in the other titration curve, and it should show an increase in spike there. All right, so however, it's a little bit different at the equivalence point here. We do have the salt, and the salt here is going to be sodium acetate. All right, and we have water. All right, there should be, at this point 3, there should be all of this should be gone, all of the acid, and all of the base should be gone. Oops, let me rewrite that a little bit better. That should be gone, and that should be gone, okay? Keep on doing the same. There we go, gone. All right, so the only thing then exists at the equivalence point is our salt and our water, okay? So again, we need to ask ourselves, what affects the pH at the equivalence point? Does the salt have any factor here? Well, if we look at the salt and the nature of it, we have a sodium ion. Now, sodium ions, they're not going to react with water. They're going to be a super weak acid. So no water reacting there. So sodium will not affect the pH. But what about the acetate ion? Okay. Remember, I'm going to draw the acetate ion right here. Oops. Draw that a little bit better. So CH3COO minus. So this is the acetate ion, which is going to be a base. Now it's a weak base. But the question is this weak base strong enough to react with water? So we do our test. And so if you recall, the acid of this weak base is the weak acid, which is essentially acetic acid. When we actually put CH3COOH, acetic acid. Now, acetic acid is not one of the 7 strong acids. Therefore, it's a weak acid, so this is going to be weak, which is why we're using it in our titration. So the question is then, is the conjugate base, this acetate ion, is it going to be strong enough to react with water? And the answer, yes. it will react with water, okay? And so therefore, since it's a base and it reacts with water, it's going to form a basic solution, all right? So that's what it means then overall. I'm going to erase this now. You don't erase that. Keep that in your notes because that's important. But now what we have here is identified that the pH cannot be 7. All right, because of the acetate ion reacting with water, the pH has got to be greater than 7. So at the equivalence point here, the pH could be 8, essentially. So we can say that at the equivalence point, the pH has to be greater than 7 because the anion will hydrolyze or react. Oops. Let me redo that. So at the equivalence point, the anion will react with water. Okay? And if you want to see that reaction here, I'll draw it here. CH3COO minus plus water. So water will be our acid. Donate to here, and we create CH3COOH plus a hydroxide ion. And of course, the hydroxide should cause an increase in the pH. Okay, so there's the reaction, just so you can see that. And of course, that's the reaction that takes place with the salt at the equivalence point. Okay. Water will also affect the pH, but not as dramatic as the anion will. So we'll just ignore water in this case. All right, so then what about point 4 now? Well, point 4 again is where we've overshot the equivalence point. So we've added an excess amount of base. So the acid, our weak acid, is still gone, but now our base is going to be in excess at point 4. So this should be the pH of the strong base, which is going to be excess, right? Excess is strong base at point 4. All right, so there is a weak acid, strong base titration curve. Make sure you know very well all of these component parts of the curve at each one of these 4 steps. All right. All right, so the next one we're going to do now, we're going to take a strong acid and we're going to titrate it with a weak base, essentially. So an example would be like HCl, our strong acid, plus a weak base like ammonia, and we end up getting NH4Cl. Okay, so we actually are just creating a salt here, more or less, in this regard. So let's take and draw a titration curve. By the way, this kind of titration is not as common as the other 2 titrations we just looked at. So again, we have the pH and then the volume of now weak base added. Okay, so here our curve, we're going to start at a low pH and then we'll gradually move up and over like so. Okay, so again we have 0.1, 0.2, 0.3, and 0.4. Okay, so 0.1 is going to again be the pH of the strong acid right now, and notice it dropped down again to a pH of 1, being a strong acid. 0.2, we're going to create another buffer here. So this is the buffer region. So at this point here, we have our buffer. Because we have a weak base is going to be more or less a basic buffer. So actually, let's do that. Let's call this a basic buffer that's being actually formed here because of the weak base. So that means that the buffer region, number 2, is going to be, again, halfway to the equivalence point. Okay, halfway to the equivalence point. And at this point, the ammonia concentration is going to equal the conjugate acid concentration, which is the ammonium ion. So these two are going to be equal to each other at the equivalence point. And therefore, at the equivalence point, or halfway to the equivalence point then, we're going to have a 1-to-1 ratio. So the, I'll draw that, I almost said pH. So the pOH is going to equal to the pKb, since we're doing with a basic buffer here, essentially. And just like we looked with the Henderson-Hasselbalch equation, since these are equal, this should be a 1-to-1 concentration ratio. All right, so that's point number 2. Point number 3, again, is going to be our equivalence point. All right, so what exists at the equivalence point is going to be our salt, which is NH4Cl in this case, and water. Okay, so all of the acid is gone, and all of our weak base is now gone at the equivalence point. And the only thing that's left is the salt and the water that the reaction occurred in. Okay? So the question is, what affects the pH? Does the salt affect the pH? And the answer is it will. All right? Now the chlorine anion here, this time will not react with water because the chlorine anion comes from hydrochloric acid, which is a strong acid. So the chlorine anion will not hydrolyze or react with water. But what about the NH3, the conjugate base or conjugate acid, or NH4? Sorry, NH4, the conjugate acid of this salt. Well, it turns out that if you look at the base and we do our test, we get ammonia, and ammonia is a weak base. So therefore, the conjugate acid here of ammonium ion, NH4 plus, is going to be strong enough to react with water. So yes, we will get water hydrolysis occurring here. Now, since the ammonia ion, NH4 plus, is an acid, okay? So NH4 plus is an acid. Therefore, it should create an acidic solution when it reacts with water, form NH3 plus hydronium ion. Okay, so we should see at the equivalence point that the pH should be less than 7 because of that acid or hydronium ion, that acid-base reaction with water. All right, so at the equivalence point then, the pH, let's write that down, the pH should be less than 7 in this case. And so if we draw a line over here, maybe it would be a pH of 6 at that equivalence point. Okay? Hopefully this makes sense. Okay? And of course, this only occurs between a strong acid and a weak base titration. All right, and then the last point, number 4, that's going to be an excess of base added. So now we have an excess of our base, and so this should be the pH of the weak base at 0.4. Okay? So here is number 3 titration curve that is possible. Study it, know it super well, okay? Now let's look at the very last one now. Now this last one is a very, very rare experiment to actually conduct, where we have a weak acid and a weak base titration. So we have our weak acid, CH3COOH, plus our weak base, we'll use ammonia again, and in this case we get the NH4CH3COO salt, okay? So this is our salt that we made, all right? So if we take and essentially graph the data, pH on the y-axis, this is the volume of weak base added. And then we're going to get a really different, strange titration curve that's going to look kind of like a mumble jumble like this, okay? And we're going to have a 1, we're going to have a 2, we're going to have a 3, and a 4, okay? Now, so number 1 should be the pH of weak acid. It might be, again, a pH of, say, 4 for the weak acid. Number 2, we're going to see the pH rise steadily. At 3, we hit our equivalence point again. But what exists at the equivalence point? Well, the only thing would be water and our salt, NH4 CH3COO, okay? Now the question is, will our salt affect the pH? And the answer is yes. We already looked at the ammonia ion is going to react with water, and that should form this plus the hydronium ion, okay? And our acetate ion, we also said, will react with water. So both the anion and the cation in the salt will react with water, to form hydroxide and hydronium ions. So it's forming both of them. So how do we detect or determine the pH at the equivalence point here? Well, we can't really. It's too difficult. So what I'm going to say here, I'm going to erase this. You don't erase this. Keep these reactions in your note to refer to. But we're going to say that at the equivalence point, the pH is too difficult to identify. All right, and you can use these exact words on the test if they actually gave you a titration curve between a weak acid and a weak base, okay? We just cannot define the pH at the equivalence point because both the anion and the cation are going to hydrolyze or react with water, all right? And then 4, this is just going to be the pH of the weak base, because after the equivalence point we've overshot it and we've added an additional amount of weak base, so it's going to be excess, okay? So again, the idea is that at the equivalence point, all of the acid is gone, all of the base is gone, nothing will be left except for the salt and water at the equivalence point. The anion and the cation both react with water, so we cannot define or identify the pH. It's too difficult at the equivalence point. But once we overshoot the equivalence point and we've added an excess amount of weak base, then the pH then becomes the pH of the weak base at that point, okay? So this is the last titration curve we're going to discuss. The first 3 are very important. The first two are very common, especially on the exam. So you need to really study the first three, and really the first two know super well. Okay, so that's it. I do want to say though, is on the test, two things can occur. They can give you a titration curve, and you will have to identify the different points, those 4 points that we've talked about, and what they mean and what they represent. But you also might have to draw a titration curve, especially on the free response part of the test, for a particular titration, whether it's a strong acid, strong base titration, or a weak acid, strong base titration, and draw in the points and identify those points, okay? So know these curves really well. They will absolutely be on the test, both the AP and the IB exam, okay? So anyway, that is it for this part of the lecture video or lesson. So study it, all these notes really hard on titrations, and that's it.